This is section 6.2. I'm going to do this video in 3 parts. The first part, we're just going to do this first page. Up at the top here, you see a free body diagram. So if you've taken physics, you might be familiar with taking a vector like gravity and decomposing it into the sum of 2 other vectors. Usually those 2 other vectors are perpendicular. And that's what we're going to talk about today. So let's start with some true false. These are all review problems, so you might want to pause it, try these on your own, and then restart the video and see how you do. Okay, number 1. The matrix definition of dot product is U dot V is UV transpose. That's false. It should be U transpose V. Okay, second one. In terms of the dot product, length of U is V dot V. That's again false. It should be the length of V is the square root of V dot V. 3 is true. If U dot U is 1, then the length of U is 1, and that's since the square root of 1 is 1. And U dot U is the length squared. If U and V are said to be orthogonal, if U dot V is 0, that's true. It's a very important definition. And it's also true that the 0 vector is orthogonal to all other vectors because 0 dot U is going to be 0 for all U. All right. 6 isn't at all obvious at first, but if you do a quick calculation, you'll see it's true. The distance between U and V is the length of U minus V, which is the length of, if you take U and subtract V, you get 2, -2, 0. And so the length of that vector is the square root of 2 squared, which is 4, plus -2 squared, which is +4, so that's root 8. 7 is false. A vector is orthogonal to a subspace W if U dot W equals 0 for all vectors W in big W. All right, and the next one's also false. W perp is the set of all x in Rn such that x dot W is 0. That's true, but it needs to say for all little w in big W. So it's missing a piece. And number 9 is true false. This part's true. Rho A perp is null A. And the next part, call A perp, this one's false. This should be null A transpose, not null A all transposed. In fact, null A transpose doesn't even make sense because this is a vector space, not a matrix. Okay, 2 important definitions. Vectors are orthogonal if they're pairwise perpendicular. So if you dot every vector in the set with any other vector and you get 0, then we say that set is an orthogonal. Orthonormal is a step better than orthogonal. It's orthogonal, but every vector in the set has length 1. So this is the last example I'll do for this page. Show U is an orthogonal set and then transform U into an orthonormal set. Okay, to show U is orthogonal, we have to show that U1 dot U2 is 0, because we have to show U1 is orthogonal to U2. So we get 1 minus 1, and that's 0. We also need to show that U1 dot U3 is 0. So U1 dot U3, I can just see that, that's 0. And then the last one we would have to check is U2 dot U3. that needs to be 0. And looking at U2 and at U3, that's 0. So we have an orthogonal set. That's part A. Part B, to transform an orthogonal set into an orthonormal set, you need to divide each vector in the set by its length. So we want U1 over the length of U1, U2 over the length of U2, comma, U3 over the length of U3. So that's the set, okay. The length of U1 is square root of 2. So U1 divided by the length of U1 will be 1 over root 2, negative 1 over root 2, 0. The length of U2 is also root 2, so this next vector is going to be 1 over root 2, 1 over root 2, 0. U3 already has length 1, so we don't need to normalize it. We can just leave it alone, 0, 0, 1. And now we have an orthonormal set. All right, so we'll finish up with the next 2 videos.